Now, I'm going to talk about fit-for loop, or FFL. Let's say we have this 3-gene network. X activates Y and Y activates Z. At the same time, this X is activating Z. We have this direct path where X is activating Z directly. And we also have this indirect path through which X is activating Z through Y. This FFL is called a coherent FFL, meaning that the direct and indirect paths have the same effect. So in this case, the direct path is activation, so X is activating Z, and indirect path is also activation. X is activating Z through Y, but it's an activation. So here I have another example of coherent FFL. So let's say we have X activates Y and Y inhibits Z, and X is also inhibiting Z. Here we have this direct path, which is inhibition, and this indirect path is also inhibition. X is activating Y, which is inhibiting Z, so the net effect is Z inhibition by X. Here we have another example. X inhibiting Y and Y inhibits Z, and X is activating Z. So what is the effect of this direct path? Activation. But here, X is suppressing Y, which is suppressing Z. So by suppressing Z suppression by Y, X is activating Z. This FFL is type 1 coherent FFL and is the most common one. Now, I want to think about the time-dependent dynamics. If you think about this simple 2-gene regulatory network dynamics, so we have this input gene activating output gene, and we can assume constant input protein levels, and this output protein level starts from here, 0, and reaches a steady state. It reaches a steady state level, let's say at this point, and there is this time delay. So what I'm saying is, even though input level reaches this maximum or steady state, output level will reach its maximum level or steady state after some time delay. That's the main point here. We are not showing these activating genes for X, but we assume that X reaches a steady state. The levels are constant. So we have this constant X, and we assume that Y starts from 0 and reaches a steady state. There should be some time delay. And when Y activates Z, this Z will reach steady state with some time delay here. So we have another time delay. This time, we have a constant Y here, but this constant Y will not make this Z immediately increase like this. We need some time, this amount of time, and then Z reaches this steady state. So we have another time delay here. So what does this mean? If X directly activates Z, and if there's no indirect path, X may quickly activate Z. Z may reach the steady state fast. But since now we have both direct and indirect path, the final Z concentration, which is a steady state, is only achieved when both direct and indirect dynamics are complete. So even though this direct path may be fast, if this indirect path is slow, the final dynamics is affected by this slow process as well. So the net effect of this type 1 coherent FFL is a delay of Z expression. And we will see later that this can play an important role in some biological applications. Now I want to talk about incoherent type 1 FFL. Here we have 3-gene network again, but this time X activates Y and Y inhibits Z, and X is activating Z directly. So direct path is activation and indirect path is this path is inhibition. That's why we have incoherent FFL, because one is activation and the other one is inhibition. We assume that X is constant. X is activating both Y and Z. So let's say this Y increases and reaches a steady state. And also we have this Z, which increases. But what happens is this. initially Z will increase, but as Y increases, Z will be suppressed. So we have what's called pulse-like expression for Z. Now, I'm going to talk about complex interlocked FFLs. We have X1 activating Y1, and Y1 inhibits Z1, while X is activating Z1 directly. This is incoherent type 1 FFL, which causes pulse-like expression of Z1. This X1 and Y1 also activate X2, and this is coherent type 1 FFL. If you look at these three genes, X1, Y1, X2, X1 is activating Y1, which is shown here, and Y1 is activating X2, which is this one, and X1 is activating X2 directly, and this network is coherent type 1 FFL. This FFL causes a delay in X2 expression. Now, X2 activates Y2, and Y2 inhibits Z2, and X activates Z2. We have another incoherent type 1 FFL, which causes pulse-like expression in Z2. And finally, this X2 activates Z3, and this Y2 also activates Z3. And again, we have this coherent type 1 FFL, which causes delay in Z3 expression. So this is again coherent type 1 FFL, which causes delay in Z3 expression. Let's draw the dynamics. We know that this G1 has pulse-like expression. And after some time delay caused by this coherent type 1 FFL, we have this another pulse-like expression, which is Z2. After some time delay, which comes from here, we have a Z2 expressed and also inhibited. And this pulse comes from this one. So this pulse comes from this one, and this pulse comes from this one. And finally, we have another delay here, and we have Z3 expression. So you see that this interlocked FFL enables sequential expression of Z1, Z2, and Z3. This interlocked FFL gene regulatory network has been reported in this paper.